So last time we left off talking about Jen and Eric's store, and we did the torque clockwise being equal to the torque counterclockwise in order to solve and find that the tension in the rope was 228 newtons. But what we didn't talk about was the fact that there was forces on the actual hinge itself. And so if we wanted to pick up and talk about that, on the backside it says, and this is on the torque notes if you are lost here from the last video, it says that what are the vertical and horizontal components of the supporting force that's provided by the hinge. And so if we think about that force, there would have to be both y components upwards opposing the tension, and then also some x forces if the system's truly going to be in equilibrium. And so to find that, the easiest way would be just to kind of sketch out our hinge here. Let's do a nice purple color. So we would have our hinge and the hanging beam, and then we had the tension out here, which we found previously to be 228 newtons. And then if we think about the force here being the gravitational force of the beam, 350 newtons they said, or that was from the sign, I guess, hanging, then that means there's got to be some y forces here in terms of the hinge in order for the system to be balanced. So if we think about the sum of forces in the y direction, that would basically just be looking in translational equilibrium, in other words, up and down equilibrium, nothing rotational. So we do the force y on the hinge plus the tension force minus Fg has to be equal to 0 if the system's not accelerating up or down, which means that the tension, or rather the force on the hinge in the y direction is equal to force of gravity, if we add it across, minus tension, which means that the force in the y direction is equal to 350 newtons minus 228 newtons, which is 122 newtons. So the hinge itself would be supporting a force of 122 newtons. And sometimes you'll see questions like this that say the hinge can only support 100 newtons. And so if that's the case, this is going to break, and then we might have an acceleration as our system flies off, or whatever the case may be. In the x direction, we'll see pretty quickly here that there's no x forces, and so everything's already in balance. That would mean that there's no x forces acting on my hinge. Now in this other example, which we'll go through, there's two students sitting on opposite sides of the 800 Newton teeter-totter. And so by giving us that information, that means that we need to think about this gravitational force of the teeter-totter being 800 newtons. So Fg sub teeter-totter. You're going to put teeter. And then we have students on either side. Student 1 says a mass of 65 kilograms, sits at the very end of the teeter-totter. And student 2 has a mass of 90 kilograms. The question is, how far should he sit in order to achieve equilibrium? So this is really similar to the lab that you guys were doing and that most of you have finished. So let's put student 1 over here. And they told us that force gravitational would be our mass. They said 65, so we can just call that 650 newtons. And then we want to know, where does M2 need to go, or student 2, in order to balance? And so if this is Fg equals 900 newtons, we know, just because we're logical thinking human beings, that this distance is going to have to be smaller than the full length, because if he's all the way at the end over here, then we're going to have a net torque, and that's not going to be good. And so thinking about my forces, let's call this Fg1, this Fg2, and then for the Fg of the teeter-totter, you could also think of that as Fg3. But ultimately the question is, how far should this student be sitting in order to balance the system? And so just like in the lab, we can think about the lever arm of each part of the system, how much torque is being provided. But in order to be in equilibrium, we know that the torque clockwise has to be equal to the torque counterclockwise, just like in the lab. And so in the clockwise direction, student 2's force, if I think about this kind of traveling just on its own, it would theoretically go in a clockwise direction. And so that means I would have the force gravitational 2 times distance 2. And that's going to be counteracted by force of gravity 1 from student 1 over here, because his force is counterclockwise times distance 1. And that distance 1 is half of 2.6, so 1.3 meters. Since they told us that he sits at the very end of the teeter-totter. And so if I were to rearrange this in terms of D2, I would have Fg1 D1 over Fg2, which means I would have Fg1 was 650 times D1, which is 1.3 meters, divided by my second gravitational force, 900 newtons. And then this is going to be equal to about 0.94 meters. When I originally worked this out, I used 9.8 like you did in the lab. And so if this is off a little bit, then that might be why. But if you do 600 times 1.3 over 900, it should be about 0.94 meters or so. And we know this has got to be right because it's less than 1.3 meters. And so that would be my finished answer. Now I want to look at one more because there's a few on the 3.2 worksheet which are a little tricky. And that's because they actually have two pivot locations. So for example, here we have a 3,500 kilogram truck. Let me draw our truck real quick. Don't judge the art. So we have our truck here, like nice flatbed truck. And in this truck, let's put a little guy. Door handle, hub. This is really beautiful. Okay, so a 3,500 kilogram truck is parked on a bridge as shown. If the bridge deck itself has a mass of 6,500 kilograms, find the supporting force provided by each of the two support poles. So that wants us to think about both of these support poles and the normal force that they're applying. So this would be Fn1 and this would be Fn2. So thinking about those two forces, gravitational force of the bridge, because they told us about the deck, so I'm going to call that, let's call that actually Fg2, and I'm going to treat the truck as Fg1. And so thinking about both of those forces, they give us the distance from the wall to the supporting beam as 5 meters. And we could reason that the distance to the center of the bridge is half of 15, so 7.5 meters. And so thinking about that, we could set up our formula of torque clockwise equals torque counterclockwise, assuming the bridge is not falling apart and it's in equilibrium. But then the problem is you don't know which side to pick. And well, the answer is you just pick one. It doesn't really matter. I chose to work from the right side because that's what they gave me the information about with 5 meters. And so if I think about this big X here as being my pivot, I know that both of these forces are providing a torque in the, kind of tracing it out again like I did before, that would be in the counterclockwise direction. And if that's the case, then the only thing supporting those forces over here in the clockwise direction would be the normal force 1. And so I would have Fn1 times d, we'll call that d3, which is the full 15 meters, would be equal to Fg1 d1, which I'm calling 5 meters. And then we would have plus, because also in the counterclockwise direction we have Fg2 d2, where d2 is 7.5 meters. And so from there, I would actually need to solve. We would be doing Fg1, which would be the force of gravity, not just the mass, but 35,000 newtons times d1, which is 5 meters, plus Fg2, so that's the full bridge, 65,000 newtons. And that's times d2, 7.5 meters. And all of that would be divided by d3, which is 15 meters, in order to solve for Fn1. And that gives me a value for Fn1 of approximately 43,300 newtons. And so from there, you have two options. We can either accept that as an answer and then go to the other side, measure our new distances, and then resolve, taking this as the pivot, or we can do a simple sum of forces. In the y direction, I know that all of my forces are balanced. And so if I take my Fn1 plus Fn2 minus Fg1 minus Fg2, that should all equal 0. And so thinking about that, that means that Fn2 would have to equal Fg1 plus Fg2 minus whatever Fn1 is holding up. So pretty much this is just a way of thinking about it as Fn2 over here, where I was solving originally, is picking up all the remaining slack from Fn1. because it's the only other supporting force in the clockwise direction. And if you're having trouble thinking about that as clockwise, think about if this is my pivot and we're thinking about how much force this is providing, this would be in the clockwise direction. And so if you go down here and solve, you would find that Fn2 is equal to the remaining amount. And so let's crunch those numbers real quick. We would have Fn2 for Fg1, we would have the 35,000 newtons plus 65,000 newtons minus the answer we just found, 43,300 newtons. And so when we plug that in, minus our 43,300, we're left with 56,700 newtons. Okay, so let's figure out if that's right. It is, but how do we know that this is right? Which force would we expect to have a greater force on it? Should Fn2 be larger or should be Fn1 larger? And the answer is, as you're probably shouting at the YouTube screen, Fn2 should be larger because the truck is closer to that side of the bridge. The bridge's weight should be evenly distributed between the two, but since the truck is closer here, it's only 5 meters from the right side, whereas over here there would actually be 10 meters of distance. That means that Fn2 should be carrying more of that torque in order to maintain equilibrium. And that's exactly what we see with Fn2 being larger than Fn1. And so a torque problem is really no more difficult than anything else we've done. It's just you have to think about direction, being clockwise or counterclockwise. So hopefully that's helpful, and we'll pick it up and talk more about the next phase when we're looking with torque not at 90 degrees.